Hello and welcome back to another Algebra 2B STEM review video. Today I'm going to be going over the exam review for the second semester. So let's get into it. So the first, I'm going to be doing this in two parts. This first part is going to be chapters 5 and 6. And then I'm going to be doing 7 and 8. Or no, 7 and 9 in the next video. So, alright. Starting with chapter 5. This is about radical equations and radical exponents. So, for the first one, we wanna change this form, which has a fractional power. Let me get my pen. It has a power of 3/2. So, instead of writing it as 3/2, what we can do. Let's see if. One second. Alright, there we go. So what we can do is, instead of writing this as 36 to 3/2, because that 3 is being divided by 2 in the exponent, that's the same thing as a square root of 36 to the third power. Because whenever you have something to the, let's say, b over c power, that's the same thing as taking the cth root of a to the b. Right, so fractional powers just mean roots. So, yeah, if you were to write this in radical form, you could do, there's two ways, the square root of 36 cubed, or you do the square root of 36 and then cube the whole thing. They're the same thing. Okay, if you were to evaluate that, I find this second option actually easier to evaluate, because the square root of 36, that's just 6, and then we're cubing that. And then 6 cubed, if I remember correctly, that's like 216. Yep, 216. Okay. So now we're on to solving. So for the first one, the big thing is just you need to know how to undo these roots. So to undo the root, what you want to do is square both sides. So you're going to get x minus 4 equals 3 squared is 9. So x is equal to 13. Now, let's just plug that back in and check. So the square root of 13 minus 4, is that equal to 3? So this is the same thing as the square root of 9. Is that equal to 3? Yes, because square root of 9 is 3, so both sides match. So notice, we could cube both sides, but notice we'd have to, if we cube both sides, we have to distribute that to both. And I think it's easier to just divide by 2 first, so we can get the root by itself. So what you get is the cube root of 13x minus 5. 10 over 2, that's 5. So now we're going to cube both sides to undo that cube root. So you get 13x minus 5 equals 5 cubed, that's 125. That means 13x equals 130, which means x equals 10. Okay. And if we were to plug that back in, just check real quick. So we're going to say 2 times the cube root of 13 times 10 minus 5. Is that equal to 10? So this is 2 cube root of 13 times 10, that's 130, minus 5, 125. Is that equal to 10? Well, this cube root of 125 is going to be 5, so 2 times 5, is that equal to 10? Yes. Just remember to always check your answers, especially these types of problems. Okay. So notice we have our root, and instead of having a number on the other side of the root, we have an x. So it's especially important when you get these kind of problems where you square both sides and then you get an x squared. Especially important that you check that you check that you don't have any extraneous solutions, because often one of them will be. Okay, so x squared minus 3x minus 40. I'm subtracting 3x and 40 from both sides. That's equal to 0. So let's think, what two numbers multiply negative 40 and add to negative 3? Oh, I'm thinking of negative 8 and 5. So, because negative 8 times 5 is negative 40. Negative 8 plus 5 is negative 3. So that works. So we can factor this as x minus 8 times x plus 5 equals 0. That means our zeros is going to be x equals 8 and x equals negative 5. You can just use that comma instead of putting another x equals. You can do x equals 8, comma, negative 5. Okay, so now let's check both of our answers to see. Remember, plug it back into the original equation. So, is 8 equal to the square root of 3 times 8, that's 24, plus 40. So that's going to be the square root of 64. Is 8 equal to the square root of 64? Yes. Alright, what about the other solution? Negative 5, is that equal to 3 times negative 5, that's negative 15, plus 40. So that's the square root of 25. So, what we're saying is negative 5 equal to square root of 25? What's the value of this? Square root of 25, that's 5. So is negative 5 equal to 5? No. So that's an extraneous solution. I'm just erasing because I need more space, but on an actual exam or test, I recommend keeping all your work, but just note, like, kind of like circling like this, like x equals 8, doing a box around it. Doing that for the right solution. And then keep the extraneous solution, x equals negative 5. And then maybe just like do a x over it and write extraneous solution. Because you still want to have the work for getting both, but you just want them the grader to know that this is the actual right solution. Alright, now for finding inverses. You can think of inverses as kind of like the opposite of a given function. So if the inputs for one function, here's an example. So let's say you have a table of values. Say we have two values at x equals 2 and x equals 4. So let's say, or not, let's do f of x. So f of 2 is negative 1, and f of 4 is negative 3. Well, we could say the opposite for the inverse, that f inverse of negative 1 is equal to 2, and f inverse of negative 3 is equal to 4. So the inverse, it just has the inputs and outputs swapped. So what you want to do when you're like algebraically solving for the inverse is you want to swap the inputs and the outputs. So we're going to swap, instead of using f of x, let's use y. So we're going to swap y with x, and then you want to solve for that new y. So what we're going to get is x equals 2y minus 1. So if I add 1 to both sides and add 1 to both sides and divide by 2, I get y equals x plus 1 over 2, which is 1/2 x, or let's just leave it as that. Okay, but remember, you generally want to use, instead of using y, you want to use f inverse. So you write as f on a little negative 1 over it, and then of x. So f inverse of x is x plus 1 over 2. Alright, let's do it for this other function. Remember, same process. Let's swap. This is our y. Let's swap the x and the y. So x equals y plus 1 cubed. Alright, so let's take the cube root of both sides. that cubed is going to cancel with the cube root. So cube root x equals y plus 1. If I subtract 1 from both sides, I can solve and get cube root of x minus 1. That is our y. So we're going to use f inverse of x equals cube root of x minus 1. We're going to use the f inverse instead of the y. Alright. Alright, just 2 more for this part. Okay, so we want to find f plus g and f minus g for these two functions, and then say their domains. So f plus g of x, well, that's just the same thing as f of x plus g of x. Okay, so this is going to be 9x plus 2x squared, that's our f of x, plus x squared minus 3x plus 7. Okay, that's 3x squared, if we combine like terms, plus 6x plus 7. Okay, that's our f plus g. So notice this is just a polynomial. In polynomials, their domain is all real numbers. So we can write, fancy r, or we could do interval notation, negative infinity to infinity. Okay. Now f minus g of x, that's just f of x minus g of x, which is 9x plus 2x squared minus g of x. So we have to make everything in g of x negative. So negative x squared, and then we turn that negative to a positive, plus 3x minus 7. Right? Because negative g of x, we just swap the signs for all of this. So, yeah. And if we evaluate that, we get, combines our x squareds, we get x squared. We combine our x's, we get plus 12x minus 7. So I get x squared plus 12x minus 7. And again, that's just a polynomial. So our domain is all real numbers, or negative infinity to infinity. Alright, now we're going to do that for multiplication and division. So, f times g of x, that's the same thing as f of x times g of x. Okay, so that's 4 times x to the 2/3. Okay, times our g of x times 2 times x to the 1/3. So if we multiply together our constants, we get an 8, and we add, well, we're multiplying x to the 2/3 and x to the 1/3. Because we're multiplying with the same base, we can add the exponents. So that's going to be x to the 2/3 plus 1/3, that's 3/3, which is 1. So it's just 8x. Now, notice, in every step of this, we didn't have any square roots, we didn't have any division by x. We only had like roots of 3, right? Radicals of 3, if you think about it. That 2/3 and 1/3. So that those functions with cube roots, they are defined for all numbers. There's not going to be any number where it's not going to work. So that means, and also look at our final function, right? Just based on the fact that this isn't a square root, we're not dividing by 0 or anything. Our domain is just going to be all real numbers, or negative infinity to infinity. Now that's often the case with multiplication, but not always with division. So f over g of x, that's going to be f of x over g of x. So our f of x is 4x to the 2/3, and then our g of x is 2x to the 1/3. Now notice, before I do this cancellation and like the simplifying, I want to know, we have in our original expression for f over g of x, we have an x to the 1/3 power in the denominator. So what that means is x is not going to be able to be 0 because that would make the denominator 0, which does not work. So our domain is x is not equal to 0, or if you want to use interval notation, negative infinity to, negative infinity is 0, and then union 0 to infinity. That just means everything from negative infinity is 0, but not including 0, and then from 0 to infinity, not including 0. Okay, so for simplifying, 4 over 2, that's 2. 2/3, for the 2/3 over, x to the 2/3 over x to the 1/3. We subtract the exponents because we're dividing. So 2/3 minus 1/3, that's 1/3. So our simplified expression is 2x to 1/3, but that only works if x is not 0 because we'd be dividing by 0, and that does not work. Okay. Now for number 9. Alright, let's get some points. For one, I want to do, for log functions, I like to have, like whatever the base is, I like to do 1 over that base. I like to do 1. I like to do the base, and then I sometimes go by powers of the base, but not always. So, let's see, 1/5. If we do log base 5 of 1/5, that's 1/5 is just 5 to the negative 1. So log base 5 of 5 to the negative 1 will just give us negative 1. Log base anything of 1 is 0. Log base 5 of 5 is 1. So 1/5 is about right there. Oh wait, no, I did that wrong. 5 would be. Okay, let's get some other values. Let's just fill this in. Let's do 8. Let's say you wanted to find log base 5 of 8 on your calculator. What you would do is, if it doesn't have a log base button, what you would do is you would do log of 8 over log of 5. So you just use the log base 10, which is the standard log. You do the log of the thing you're taking the logarithm of divided by the log of the base. That's the change in base formula. So if you were to type log 8 over log 5 in your calculator, I get 1.29. So about right there. If I want to do it for 3 as well. So in my calculator, I would type in log of 3 over log 5. I get 0.68. Alright, so the way you kind of want to graph this, assuming you don't have any translations or anything, you want to have your asymptote is going to be at x equals 0, right? This along the y-axis. So it's going to be going down, not touching it, but it's going to be getting really, really close. It's going to be coming up, and it's kind of slowing down, if that makes sense. Like it's flattening out. So you just try and connect your points like that. And yeah, as long as you have your points, you should have a pretty accurate graph. So the domain is x greater than 0, right? 'Cause it doesn't work for, it's not equal to, because it can't be equal to 0, because of that vertical asymptote. But it can be everything greater than 0. The range, notice this is going to keep going this way, and it's slowing down, but it's also going to keep going this way, upwards. So it's going to be negative infinity to infinity, or, the fancy r. That's going to be our range. And then, again, we have an asymptote at x equals 0. Okay, So for 1/4 e to the x, for any exponential function, the domain is going to be all real numbers right off the bat. The range, well, let's do that after we do some graphing. I think I'm just going to do some points. Okay. So if we plug this into our calculator, we would do well, you could just type the whole function in your calculator. For this, I get 0.0338. For this, I get 0.091 or 92. For this, it's going to be 1/4 times e to the 0. E to the 0 is just 1, so 1/4 times 1, that's 1/4, or 0.25. And then e, when we have 1, that's going to be 1/4 times e to the 1, so it's 1/4 e. So 0.6796. And then for 2, that's 1/4 times e squared. And that is 1.85 about. Alright, now we have some points. So at 1, it's going to be at 0.25. Sorry, 0. Alright, you can kind of just graph these points now. Oh, I think I can get one more point at 3. Let's see, at 3 it's a little over 5. So it's 5.021. Alright, I think that's enough. Alright, and then just have it going down close to that that horizontal asymptote, but not touching it. So yeah, exponential functions, remember they have that horizontal asymptote. If they're not vertically translated, it's at y equals 0. So notice, this function, it has output values that are all greater than 0. So our range is y greater than 0. So it's not going to equal 0, but it can be anything above it. And we have a horizontal asymptote. It's flipped. Think about it. Horizontal means use y equals. So y equals 0 is our horizontal asymptote right here. Alright, number 10, we want to expand the logarithm. Okay, so log base 4 of 8x squared. Now, remember, when you have a logarithm and you're multiplying on the inside, you can split it up and add on the outside. So what I mean is, this is going to be the same thing as log base 4 of 8 plus the log base 4 of x squared. Okay. So now I'm going to simplify this a little further. So, let's think. So log base 4 of 8, that's the same thing as log base 4 of 4 times 2. So I can split this up even more. Log base 4 of 4 plus log base 4 of 2. Well, 2 is just 4 to the 1/2, it's square root. So log base 4 of 4, that's 1. And then plus log base 4 of 4 to the 1/2, this will cancel out, so that's just 1/2. So 1 plus 1/2, that's 3/2. Okay, so we're good with that number. Now with this x squared, when you have log of a to the b, you can pull that down that b, so it's going to be b times log base a. Sorry, just log of a. So we can pull down this 2 of the x squared, and it's going to be plus 2 log base 4 of x. Okay, that is the final answer. Now we're going the other way. So let's just use that in reverse. First, before we can do our logarithm, like combining with the adding, we want to bring this x on the inside. So we have an x over here on the outside, but that's the same thing as if you're just having it as a power on the inside. So it's the same thing as log base 3 of 8 to the x plus log base 3 of 1/2. Now log base 3 of 1/2 plus, adding these things together on the outside, it's the same thing as multiplying on the inside. So it's the same thing as log base 3 of 1/2 times 8 to the x. That is our final answer. Alright, now evaluate the logarithm. This one, usually when it's logs, you're not going to be able to, when it's natural logarithm, usually you have to use a calculator to get like a number for it. You could rewrite this and be like, okay, this is natural log of 2 squared times 3, if you break it up. So that's 2 natural log 2 plus natural log 3. But when saying evaluate, it usually wants a number. So if you were to put that into your calculator, you would get about 2.485. You could just put the original into your calculator, but I'm just showing you how you can break that apart. Alright, now for solving. With these kinds of problems, you usually want to get the same base. So think, we have a 4 over here. That means we're probably going to want a 4 or a 2 on the right side. I think I'm going to roll with a 4, because 16 is a really nice power of 4. It's just 4 to the second power. So 4 to the 5x minus 2, that's 4 squared. Because we have the same base on both sides, what we want to do is we want to cancel out that base, and then we're just left with a nice linear equation. So 5x minus 2 equals 2. If we add 2 to both sides, we get 5x equals 4. So x is 4/5, or 0.8. And again, you should probably plug it in, plug it back in, but for sake of time, I'm not going to do that. Alright, 100 to the x equals 1/10 to the x minus 3. I'm thinking we can get a common base of 10 in both of these. Think about it. 100, that's just 10 squared. That's to the x. 1/10, that's just 10 to the negative 1, because the negative exponent means you're dividing by whatever the exponent is. So this is 10 to the negative 1 to the x minus 3. Remember, we can use our property. We can multiply those, right? So this is 10 to the 2x, 2 times x, equals 10 to the negative 1 times x minus 3. That's negative x plus 3, right? Okay, now we have the same base, so we can do our trick and we can cancel both of them. So we're left with 2x equals negative x plus 3. If we add x to both sides, we get 3x equals 3, which means x is equal to 1. Alright, this one, we're going to take, we have 5 to the x equals 33. We're going to take the log base 5 of both sides. So we're left with is x equals log base 5 of 33. Or you could write this as, it's 3 times 11. So it's log base 5 of 3 plus log base 5 of 11. Either way, if we want to give an approximation for that, if you're doing your calculator, that's the same thing as log. If you use change of base, that's log 33 over log 5. I get about 2.173. Okay. Alright, just this page left. Alright, now we're going to, instead of solving exponential, we're solving logarithmic. So, when you're undoing exponents, you use the logarithm, right? I probably should have introduced that. But when you're undoing logarithms, you want to do the exponents, right? So, we have this log base 4 of 10x plus 6. Now we want to make both sides have a base of 4 of the exponent. You can do that because you're doing it to both sides. So, this is going to cancel with that log base 4. We're going to get 10x plus 6 equals 4 to 1. That's 4. If I subtract 6 from both sides, I get 10x equals negative 2. Where x is negative 2 over 10, which is negative 1/5. Always remember, plug it back in, but I'm not doing that for the sake of time. Alright. Natural log of 3x minus 9 equals natural log of 2x plus 6. Now, okay, so we're going to we have both sides of the base of e. Okay, so that will cancel out the natural log, because natural log, that's just log base e. Okay, so 3x minus 9 is equal to 2x plus 6. If I subtract 2x from both sides and add 9, I get x equals 15. Wait. Yeah, x equals 15. Now, with this one, I'm going to try and actually plug it back in. I'm just going to evaluate what's under the logarithm to make sure that it's not negative. So, 3 times 15 minus 9, that's 45 minus 9. That's positive, so we're good. Remember, you can't have negatives underneath the logarithm. 2 times 15 plus 6, that is also positive. Okay. Alright, number 18. We're going to rewrite this into the other form. So log base 3 of 9 equals 2. The opposite of that would be saying, okay, if you take the log of 9, that's 3. Another equivalent way to say it would be that 3 to the second power is equal to 9, right? Because if you have both sides of the base of 3, you think about it, this will cancel out, and you'll be left with 9 equals 3 to the second power. The opposite thing is if 6 squared equals 36, if you take the log base 6 of both sides, you get 2 equals log base 6 of 36. And that's also an equivalent statement. Okay, number 19. Alright, this one you need to combine solving with a little bit of logarithm properties. So, we're subtracting natural log of 3 on the outside, right? So we have subtraction on the outside. That means division on the inside. So this is the same thing. Natural log 4x plus 1 over 3 is equal to natural log 5. So we have natural log on both sides, so we can cancel that natural log out. We're left with 4x plus 1 over 3 equals 5. If I multiply 3 by both sides, I get 4x plus 1 equals 15. Okay, so if I subtract 1 from both sides, I get 4x equals 14. If I divide both sides by 4, I get x equals 7 over 2. Okay, let's just do a quick check. Natural log of 4 times 7 over 2 plus 1 on the inside minus natural log 3, is that equal to natural log 5? So, natural log 4 times 7 over 2, that's 14, plus 1, minus natural log 3, is that equal to natural log 15? So, natural log of 15 minus natural log 3, is that equal, sorry, not natural log 15, natural log 5 on the right. Well, remember we can use our property, natural log 15 over 3, because we're subtracting the outside. Is that equal to natural log 5? Yes, because this is just going to be 15 over 3, that's a 5. So this is natural log 5 equal to natural log 5. Yes. Alright. A couple more. Alright, so for this first one, the way that I know immediately just after looking at it, that's exponential growth, is because this b value, this growth factor, is greater than 1. So, exponential growth. Right, the percent increase or decrease in the value of a coin. You might be tempted to say, oh, 106% increase. No. Actually, your percent increase is going to be 6%. Because this on the inside, this b value, this is 1 plus your percent increase. Or if I can write it this way. It's 1 plus or it's 1 minus. Here it's plus because it's adding. So this 1.06, that's 1 plus our percent increase, right? If you look at your formula. So this means our percent increase, it has to be 0.06. Or not our percent increase, but just our increase, right? And as a percent, 0.06 is 6%. So remember, whenever you have like 1.06 or 1 point whatever, you need to take 1 away from that to get to the actual increase or decrease. And then if you have 0.06, that's the same thing as 6%. Alright, the original value of the coin, this tells you the original value. Because if you plug in t equals 0, this becomes 0. So 1.06 is 0, that's just 1. So this 0.25 just becomes the value when t is 0. In general, this thing out in front is always going to be your initial value. So 0.25, this is in dollars, so, or you could say 25 cents. Estimate when the value of the coin will be 0.6 cents. Sorry, $0.6. Well, we could estimate it, but the way I'm going to do is actually solve it. So 0.60 equals 0.25 times 1.06 to the t. We want to solve for t when our y is equal to 0.6. So before I can take the logarithm, I want to divide both sides by 0.25. Okay, so that's going to cancel. Okay, I get not 0. I get 2.4. Okay. Now I can take the log base log base 1.06 of both sides. So I get t equals log base 1.06 of 2.4. Now for most calculators, or not most, but a lot of calculators, you can't just evaluate with that kind of base. You would have to change of base. Log of 2.4 over log of 1.06. Okay. I get 15.02. So about 15 years. Okay. Now for the final question, we invest $4,000. That's our initial amount, our principal. So for our first, we want to find the amount with 5% annual interest semi-annually compounded. And then we want to see what would the balance be after 2 years. Okay, so we know our initial amount is going to be 4,000. That's going to be the thing out in front. On the inside, we're going to have 1 plus our rate, which is 0.05 because it's 5%. You do 2 decimal places back, so that would be 0.05. And then you divide that by 2 because semi-annually means twice a year. And that means n would be 2. In your formula, your n value, which is the thing you're dividing by over here, the n would be 2. So we're going to be doing 0.05 over 2. And then our n value, we also have a 2 up here, because that's our n value. And then times our t. Now we know our t is 2 years, so this is also going to be 2. So 2 times 2, that's the same thing as 4. Okay, so if I evaluate what's under here, 1 plus 0.05 over 2, I get 1.025 to the fourth. So if I raise this to the fourth, and I multiply by 4,000, I get, remember you have to have the correct units, which is dollars, so 4,415, and then 25 cents. Okay. Now for the second part, we're talking about annual interest compounding continuously. Okay, so after 2 years, we want to find the balance. And this time, instead of 5% annual interest, we have 4.5. So our amount is going to be our principal, which is 4,000, times, this time, because it's continuously, we have a base of E, and then RT, our rate times our time. So our rate, we have 4.5. Remember, move that decimal place 2 back. So that'd be 0.45 and then 0.045 times 2. That's the same thing as 0.09. So what I'm going to do is I'm going to do e to the 0.09 and then multiply that by 4,000. So I get 4,376 and then 70 cents. Alright. So hopefully that all made sense. I will post the second part soon. Yeah. Alright. Hope you have a good day.